So welcome digitally to this hybrid workshop. And we see you very well in our large lecture hall. And so let me introduce you as the first speaker of the morning session. It's my pleasure to announce Ryushi Goto from Osaka University. And well, we see the title. So Matsushima-Lichnerowicz type theorems of generalized scalar manifolds of symplectic type. That's how it is going to be. So thank you very much. And the floor is yours.
Well, thank you very much. So first of all, I'd like to thank the organizers inviting me to talk the workshop of special geometries of Riemannian Manifolds. In particular, Professor Bestia Apostrophe, I'd like to thank. So the title of my talk is Matsushima-Lichnerowicz Matsushima-Lichnerowicz type theorem. So Matsushima-Lichnerowicz theorem is a very famous theorem in Kähler geometry. It is well known. This theorem is a kind of the obstruction theorem to the existence of the scalar curvature constant Kähler metric. If the Kähler manifold admit compact Kähler manifold admit scalar curvature constant Kähler metric, then automorphism group of the scalar curvature constant Kähler complex manifold is reductive legal. Strictly speaking, so reduced one. Reduced one is reductive. So this is very firstly discovered obstruction to the existence of scalar curvature constant Kähler metric. For instance, so CP2, complex projective space CP2, does admit Kähler metric. Of course, it is well known that the Fourier-Study metric is just a constant scalar curvature Kähler metric. However, one point blown up at CP2 does not admit scalar curvature constant Kähler metric. It is because the automorphism group of the CP2 blown up CP2 is not reductive. So that this is very outstanding obstruction. Matsushima-Lichnerowicz type obstruction is very clear obstruction, I think. So today's talk, so I'd like to extend this kind of obstruction to the case of the generalized Kähler manifold. So this is a typical example of the case of the CP2. CP2 does have the complex manifold Kähler structures, and we can deform the Kähler structure of the CP2 ordinary one to deform to the non-trivial general Kähler structures. Such a deformation is given by formal Poisson structure. So from Poisson structure, in this case, this is complex surface, so that this is just a section of the anti-canonical divisor. So this is just a cubic curve on CP2. So that does it mean that each cubic curve gives rise to the deformation of non-trivial general complex structures or general Kähler structure? So that the cubic curve on the CP2 is also well known, divided it into nine classes. So this is a figure 1, 2, 3, 4, 5, 6, 7, 8, 9. And this figure is just this round one is just a CP2, and this one is just a smooth elliptic curve. Also that this one is just a nodal curve that is with singularity. Also this is a cusp one, and blue one is just automorphism group of the generalized Kähler manifold, general complex manifold is reductive. So obstruction does not vanish. Yeah, but the red one, figure 7 and 8 and 9. In this case, so this is a very special configuration of the cubic curve. So that the three, it's just a three line intersect at one point. Also double line and one line, also triple line. This is a very degenerate case. But in this case, automorphism group is not reductive. So we have actually this Matsushima and Lichnerowicz type obstruction of general Kähler structure with constant scalar curvature in this case. So this is a very typical example. So I'd like to give a plan on my talk. So first part, I'd like to define the general scalar curvature of general Kähler manifold. As already, so you already give a talk about general Kähler structure, and also Jeff gives a very nice talk on general Kähler manifold. So there's no good notion of the reductivity connection in generalized complex geometry, general Kähler geometry. So we need to consider the good definition of the scalar curvature or rich curvature. So I'd like to define the scalar curvature by using pure spinor. I'd like to explain later. And then the key points there's a moment map framework on this geometry, and then there exists a moment map, and which is given by general scalar curvature. So then we can consider the kind of the existence problem and also non-existence problem of the general Kähler structure with constant scalar curvature. Then I'd like to construct kind of the obstruction, Matsushima-Lichnerowicz type of obstruction theorem of the real algebra of automorphisms of the general Kähler manifold symplectic type with constant scalar curvature. Also, the final part of my talk, I'd like to construct general Kähler manifold with constant scalar curvature by using deformation. So the deformation starting from the ordinary Kähler manifold with constant scalar curvature. Then we can have a very nice deformation theory to obtain the general Kähler manifold with constant scalar curvature. So that is from my talk. So I'd like to give us some historical introductions. So that is a moment map and the curvature, about the moment map and curvature. So Atelier about 1980, so consider the kind of the moment map framework on the vector boundary of the Riemannian surfaces. We consider the vector boundary of the Hamiltonian vector boundary of the Riemannian surface sigma, and then consider the Hamiltonian connection on vector boundary. Then the space of the Hamiltonian connection admit can be considered as a section of the this sigma tensor unitary endomorphism of E. Then this infinite affine space admit a simplex structure, which is given by like that. Then unitary gauge group act on it, preserving the simplex structure. Then it turns out that the moment map so exists, and moment map is also that just given by the curvature. This is very important. So, but this kind of starting point relation to the moment map and the curvature. This is in the case of the vector bundle, but this kind of the result generalized to the case of the Kähler manifold by Fujiki and Donaldson. And then so they show that scalar curvature also arises as a moment map in Kähler geometry. And this kind of the result also can be generalized to the generalized Kähler geometry. And Hitchin and Galtieri introduced general complex structures and general Kähler structure. And so, Boulanger introduced generalized Kähler structures. Consider the toric general Kähler structure of simplex type, and consider the scalar curvature as a moment. And also myself consider the general scalar curvature of simplex type, and also H-twisted general Kähler structure. That's the general one. Then we show that the scalar curvature also arises as a moment. So I started by some linear algebra. So this is a very fundamental one. So Kähler structures consider the real vector space V of dimension 2n, and I is just a almost complex structure which satisfies the following, and omega is a simple structure on the vector space V. And if almost complex structure is omega compatible, so if and only if this satisfies the following, then consider the omega compatible complex structure, almost complex structures. Then this space is just a homogeneous space, SP2nr divided by un. So, and this is also given by the bounded domain. So this is just a Ziegler space. This is an n times n complex matrices, and satisfies the identity minus S A star is a positive, and also S is symmetric. So this is in the case of n equal 1, this is just a bounded complex ball, complex one-dimensional ball. So with radius 1. So that is very natural object. So then we consider the simple question. So what happens if we consider the if we drop the condition A is symmetric, this condition. If we drop this condition, then then we can consider the this kind of space. A is a matrix, complex matrices with satisfying this condition, only this condition. Then this space is also homogeneous space, un point n, and divided by un cross un. And so this is a bounded symmetric space, including the Ziegler space. So Ziegler space included this. So this is kind of the extended one, extended Ziegler space. And so this Ziegler space is just a moduli space of the omega compatible almost complex structures. So does the symmetric space of this one arise as a moduli space of some kind of geometric structure? So this is a simple question. Then the answer is yes. So then this is just given by generalized Kähler structure. So this bounded domain also parameterize compatible generalized Kähler structure. So that the generalized Kähler structure naturally appears as a generalization of the Ziegler space. So I'd like to explain more. So this is a basic element, basic factor of the generally complex and general Kähler structure. So we started by manifold of 2n dimension of 2n, and consider the tangent space plus cotangent space, where v1 and v2 and tangent, theta 1 and theta 2 is one form. And consider the bilinear form. So we consider coupling between tangent and cotangent, and consider this kind of symmetric bilinear form of the signature 2n.2m. This is indefinite one. Then the almost generalized complex structure, shortly we said almost GCS, is just a section of the SO bundle of Tm plus Ts star, satisfying the J squared is equal minus identity. So that as in the case of the ordinary almost complex structures, so then the generalized complex structure gives the eigenspace decomposition like that. And Coulomb bracket. So Coulomb bracket is a natural bracket of the Tm plus Tm star. So there is very systematic construction of this kind of bracket. So that Nyhan-House bracket or Schouten bracket and so on. This is one of them. So that this is just So that E1 is just a vector plus one form. Also E2 is a vector plus one form. And consider the Coulomb bracket is just this is just ordinary bracket of the vector field. And this is the one form, part of the one form. This is tangent. This is the cotangent. This is a Lie derivative. And also this is the interior derivative and the exterior derivative. So, and almost GCS is integrable if this sub-boundary, eigenspace boundary is involved, closed under the Coulomb bracket. Then the integral of almost GCS called the generalized complex structures. So this is the definition of the generalized complex structures. So as we know that ordinary complex structures I and give the almost complex structure of the cotangent bundle, and this diagonal matrices gives rise to the generalized complex structure. Also, symplectic structure omega gives a map from the tangent to cotangent bundle, and then this map is a identity map. So we have a natural inverse, omega hat inverse. So by using omega hat inverse, so we have this kind of matrix of diagonal matrix. So this of diagonal matrix of this endomorphism of Tm plus Tm star gives rise to the also generalized complex structures. And the integrability coming from the closeness of the d omega equals 0. So so that this is a very typical two extreme cases. So also there is a not intermediate structure that is kind of the hybrid between complex structures and symplectic structures. So generalized Kähler structure is a pair of the general complex structures J1 and J2, and consisting of two commuting generalized complex structures J1 and J2, such that G hat is this one, gives a positive definite symmetric form like that. So then we call the G is the generalized metric. This is a metric of Tm plus Tm star. And this also the general metric, so gives rise to the consists of the pair of the Riemannian metric and real two form. So this is the definition of general Kähler structures. And as I explained before, so let X be a Kähler manifold, and then there's a general complex structure JJ, and also general complex structure J psi. The psi is just this one. Well, this is general complex structure coming from the simple structure. Then the pair of the JJ and J psi give general Kähler structure. This is very typical. So also that if the action of the B field, there is the action of the B field. So let J1 and J2 be a general Kähler structure. Then the B is a D-closed two form. Then there is action of the D-closed two form and diagonal action. Also, we can have a general Kähler structure. Also, there is a very interesting general Kähler structure. So this is called the general Kähler structure of the symplectic type. So this is a pair of the general complex structure J and J psi. J psi is a general complex structure induced from the D-closed non-degenerate pair spinel. Psi is the EB minus square root minus 1 omega. And so that this is called the general Kähler structure of symplectic type. So then we have a natural construction way of the construction of the general Kähler structures of the of symplectic type. So let MJ be a compact Kähler manifold with homomorphism structure beta. Then so this homomorphism structure gives deformation of the general complex structures, and also we have a deformation of the J psi. Then as a result, the pair become a general Kähler structure of the symplectic type. So that every compact Kähler manifold with non-trivial homomorphic Poisson structures admit a non-trivial general Kähler structure of symplectic type. So there are so many examples of general complex and general Kähler structures. So in order to explain the scalar curvature of the general Kähler structure, I need to explain the Pierce-Spinner formalism. So, and phi is a differential form on the open set of the U, and consider the T U plus T star U, and so that this is V plus theta. Then the E is act on the differential form by interior product of the vector V and the exterior product of the one form theta. Then we have this kind of include identity. Then it follows that the Clifford algebra du plus T star U act on the space of differential forms. Then we have a kind of the action representation of this Clifford algebra. This is just a spin representation of the Clifford algebra. So that we have a notion of the Pierce-Spinner, and then define the kernel phi is just an element of the E, E dot phi is equal to 0. We consider this kind of space. This is an isotropic subspace. Then the phi is the Pierce-Spinner if this kernel phi is a maximal isotropic. That is the dimension of the kernel phi is a 2m. So also the Pierce-Spinner phi is a non-degenerate if kernel phi and the complex conjugate kernel phi bar is trivial. So such a non-degenerate Pierce-Spinner is very important. So the non-degenerate Pierce-Spinner phi gives our almost general complex structure by setting kernel phi is Lj phi and kernel phi bar Lj phi bar. So then we have a
hello, Ryushi?
Hi, yeah.
Can you hear me? Oh, good.
Yes.
Okay. Can you go back a few lines? I'm a bit confused. So first of all, the phi can be a differential form of any degree?
Any degree.
Okay.
So we mix the degree. So we don't mind we don't fix the degree of differential form.
Okay, so I understand you have just a representation of the Clifford algebra, which is the classical spin representation. What would be the reason to call phi then a spinor? I mean, it's a differential form.
Yes. So that the space of space of the form can be considered as a spinor representation, space of the spinor representation of the Clifford algebra by using interior product and exterior product.
Right, but you're not using Clifford product.
Yeah, Clifford product is given by ordinary interior product and exterior product.
Right, so you use the operations on spinors to define the Clifford product, right?
Yes, yes. So that we consider the T tangent plus one form. Right. Pair of the tangent plus one form.
So that the assumption on the underlying manifold is mine doesn't have to be spin. This is just totally algebraic.
No, I don't assume anything. It's just a manifold. It's just a different. It's just a differential manifold. They are differential manifold.
But only locally. It doesn't
only locally.
Defined globally.
Yes, this is just our linear algebra. So that's the way. This is a local description. But we don't assume any. M is not a spin in general. M is ordinary manifold, differential manifold.
And more only, it's not a section because not a global section because it's only defined on U. It's a very suggestive name, and suggestion is at least misleading from my intuition.
We don't need any Riemannian metric or spin structure. We only differential manifold. We only use a differential manifold and only use a exterior product and interior product, exterior product. Then this tangent plus cotangent, this space is just so that there is a natural action, Clifford action on the differential space, differential space of the differential forms. Then we have this kind of the identity. E dot phi and E dot phi is just given by coupling between E and phi. This is just a relation of the defining relation of the Clifford algebra. So that the tensor algebra act on it by this one. Then this identity gives rise to the quotient algebra act on the differential form. Then the quotient algebra is just a Clifford algebra. So that there is natural representation of the Clifford algebra on the differential forms. Okay,
Yes, thank you. This is sufficient. Thank you very much.
Yeah, you're welcome. So that we have a natural notion of the pure spinner, and also we consider the complexified vector space, so that we can consider a complex conjugate, and so that we can define the non-degeneracy condition of the pure spinner. That is, then we have a natural one. Non-degenerate pure spinner phi gives almost a GCS like that. And conversely, so almost every GCS arises as a J phi by the non-degenerate pure spinner phi. So that set of the almost GCS is coincide with the set of the non-degenerate pure spinner modulo positive constant, modulo constant. So that if J phi and J phi prime, then the phi pure spinner phi prime is equal to E phi phi, and so that for function f. So that's the set of the phi satisfying the J phi of J, define the complex line bundle, which is called the canonical line bundle Kj. So that so let D the differential operator. So phi is a differential form, so that we have an exterior derivative. Then the d phi is written like that. Where eta is just du plus t star u, and n phi is just this one. So that then the integrability of the J is with respect to the Coulomb bracket is given by n phi. N phi is equal to 0. N phi function. This calls a 9/2 tensor. So also we have an inner product of the spin representation, which is given by like that. Where alpha and beta is just a differential form. I consider the sigma beta. Sigma beta is a natural involution of the pure spinner. So we converse the order of the, if the beta is like E theta 1, which theta 2, which theta n, then the sigma beta is just a theta n, which theta n minus n, which theta 2, which theta 1. Then we consider this kind of product and taking the top degree to n degree. This is called the spinor inner product. And this one is a component of degree 2n of differential form of this one, and sigma is a, so that is a growth multiplication, like that. And so I'd like to give the definition of the scalar curvature of the generalized Kähler structures. So let M be a manifold of 2n, dimension 2n, and omega be a simplex form M, and be a real 2 form. Then we consider the psi. Psi is exponential b minus square root minus 1 omega. This is given by like that. This is a non-degenerate pure spinor, typical one. And consider the almost GCS of simplex type on M, and consider the open cover of the M. This is local trivialization of the canonical line bundle of the Kj phi. So then we assume the following normalization: spinor inner product phi and phi alpha, and psi bar. This is equal, and this Then we defined this one is a volume form. Then, as shown in the sixth one, we have this kind of the relation. Then the scalar curvature is defined by like that. Eta is act on the psi bar by Clifford in a product, and consider the exterior derivative, and take the Clifford inner product between psi alpha and d eta alpha psi alpha. Then this is just taking the real part of this one. Then we can define scalar curvature like that. So in the typical case of if generalized Kähler structure coming from the ordinary Kähler manifold, Kähler structure, then this coincides with the ordinary scalar curvature. So also I need to say that this scalar curvature does not depend on the choice of the local trivialization, the canonical line bundle. And if the J psi coming from the ordinary Kähler structure, then this one coincides with the ordinary scalar curvature, absolute constant. And I need to say so many things. So that D0 diff not M is an identical component of diffeomorphism group of deformations, and then consider the extension of the diffeom not M children extended by D equal 2 form. Then this scalar curvature is equivalent under the action of this extended one. So like that. So where G is the EBF and B is the 2 form here, and F is a diffeomorphism here. Then this so that this scalar curvature is invariant under the action of the B field. Also, this is equivalent under the action of the diffeomorphisms. So I need to explain the moment map framework. So let me go. So I've considered a compact generally complex manifold, and psi is just a symplectic type, and we pick the volume form is like that. And J is a J psi compatible almost generally complex structure. So that pair of the J and the J psi is almost generally Kähler structure. Consider the set of the generalized complex structure, which is a J psi compatible one. So that each point X, so then this space is just a fiber bundle of the fiber is just a U n point n divided by UN cross UN. This is a bounded symmetric space, as I explained before. That this is just a space of the generalized complex structure compatible with one fixed one. So that this fiber bundle, so consider the section of this fiber bundle, and then the global section of this fiber bundle, and then there's a natural symplectic structure under this section, just special section like that. So J1 dot and J2 dot is just a tangent of this space of the sections, so that we consider the let me explain. So infinite dimensional space of beta J psi M. This is a set of the sections of the fiber bundle, and fix J. And J1 dot and J2 dot is just a tangent of this infinite dimensional space, and consider the composition J1 dot, J2 dot, and J act on it, and taking the trace between them. Then integrate of this one, so then we have a kind of a symplectic form on this infinite dimensional manifold. And the complex structure is given by the just action by J. So that J is endomorphism, so acting on J1 also gives another tangent. So that we have a natural almost complex structure of this dimensional space. So as I explained before, that C infinity function, some with normalized condition, then we consider a kind of Hamiltonian Hamiltonian vector field, Hamiltonian element. This is not vector field. This is included one form. So this is kind of a generalized Hamiltonian, and then this generalized Hamiltonian is a real algebra with respect to Coulomb bracket. Also, this action of this Hamiltonian acted on the J psi, so that the J psi is invariant, this action. So does it mean that we have a infinite dimensional symplectic manifold, and so this is the Hamiltonian element, general Hamiltonian space, Hamiltonian element. So acting on it, preserving the simple structure, so that we have a kind of the position to obtain, define the moment. Then so that we can show that there exists a moment map like that, and the moment map is given by scalar curvature as I defined before. So this is a kind of the result of the. Of course, this is generalization of the ordinary Kähler manifold. So in the Kähler case, so we can define the scalar curvature as a moment. And also generalized Kähler case, so we can define the scalar curvature. So, and the scalar curvature naturally appears as a moment. In this talk, so we restrict our discussion to the general Kähler structure of the symplectic type. So this is a very restricted one, but we can extend our discussion to the more general generalized Kähler structures. So for H-twisted one, and also we can obtain the notion of scalar curvature, and also can be shown that the scalar curvature arises as a moment. So,
can I ask something?
Yeah.
Mario Garcia Fernandez speaking. Yeah, in your theorem, the volume is the one of the symplectic structure that you're fixing, or?
Yes, that's the point. And so, okay. In this case, so we fix the volume form is just given by fixed symplectic one. So that's we fix the volume form. This is fixed.
Okay, thank you.
This is point. So we can change the volume form by using some function. Then we can another kind of scalar curvature appears. So that point. And so I can say, Bourlange also obtained the moment map on the case of the toric generalized Kähler manifold symplectic type, and so Bourlange's description. So she used toric geometry, but also Bourlange's description of map seems to be different from the others one who use a Pierre spinner. But so this should be much because this is a moment map. So moment map is unique after module constant. So in fact, Bianco 1 actually shows that these are the same as using explicit calculation. Also, I need to say, so there's a one-to-one correspondence between bi-Hermitian structures, I plus, I minus, G and B. So general Kähler structure is just coincide, just gives rise to the bi-Hermitian structures, I plus, I minus, G and B. Also, bi-Hermitian structures, so satisfying certain conditions, also gives a general Kähler structure. Where G is a Hermitian metric, and I plus, I minus are complex structures, and G is a Hermitian with respect to the both I plus and I minus. So this is called a bi-Hermitian structure. So supergravity theory, so the notion of general scalar curvature is introduced. So, and so that Mario Gracia Fernandez, so such as so general scalar curvature is given by scalar curvature plus Laplacian and normal df and normal db, and surprisingly dimension 4. So Bourlange shows that so our scalar curvature is just coincident generalized scalar curvature. So the point is here. So we need to take the function f in the special way. F is just given by minus half of the log 1 minus p. The p is the so-called angle function. Then our scalar curvature coincides with the scalar curvature in the supergravity theory. So I need to say, go to the obstruction theory, Matsushima-Lichnerowicz type. So I don't have enough time. So let J be generalized complex structures on M, which gives the decomposition of the eigenspace decomposition. And then we have a kind of differential complex, which calls a algebraic complex. This is a kind of generalization of the Dolbeault complex of the complex manifold, and some composition of the Dolbeault complex. And so this is started by this is a function and wedge 1 and wedge 2 and wedge 3 and finish at ended by wedge n bar. And then this complex is also considered as a deformation complex of the general complex structures, and this part is correspond to the deformation. This is the infinitesimal tangent, and this space is correspond to the obstruction space, to the deformation. And in today's talk, we consider that this wedge 1. We denoted by H is just a cohomology groups, and so that first cohomology group H1, then consider the Coulomb bracket. Then this space is closed with respect to Coulomb bracket, so that this space the isotropic, also isotropic, so that this cohomology group inherit the natural structure of the Lie algebra, which induced from the Coulomb bracket. So in fact, we have this kind of identity, so that this cohomology group does have a very nice structure of the Lie algebra. So we denote this Lie algebra by gauge sub j, which is called the Lie algebra, the automorphism of the generalized complex manifold. In the case of the ordinary complex manifold, this is does not coincide with ordinary holomorphic vector field. We need to consider holomorphic vector field plus one form, declosed one form, H01. H0M tangent plus H1 and O. So this is slightly different. So, and also we need to consider some reduced automorphism groups. So the algebra. So this is the J psi is just another general complex structures. So we consider the function U, complex function, and consider dju and J psi act on here, and consider this is the condition, and consider this kind of element in the here. So psi in the psi is the ordinary simplex structure. So this is we consider the Hamiltonian holomorphic Hamiltonian vector field. So that this condition implies that this is the holomorphic Hamiltonian vector field. So we consider, and the U is a potential of the holomorphic Hamiltonian vector field. So that we consider this kind of space and consider the quotient space like that. Then take the image of the K not tilde to Kj. So that this then we define the K naught to be the image of the JK tilde, and then we can show that this K naught is also the subalgebra of Kj. So we call that the K naught is called the algebra of the reduced automorphisms of the general Kähler manifold. And also we can consider the real part of the reduced one. So we take the U is just a complex function here, but we use a real function here like that. So that real this get not real is just also real algebra. And then this is a definition of the reductive Lie group that I'd like to skip. So that it's a point. One of the point is just a real part of the real real algebra G not real is always a reductive Lie group. For the compact generalized Kähler manifold symplectic type. This is just a G0 real, just corresponds to the isometric group of the generalized Kähler manifold. It is well known that the isometric group of Riemannian manifold is a compact Lie group, and also that in the case of generalized Kähler manifold, generalized Lie group or generalized isometric group is also compact Lie group. So that we have this kind of result. So that this is structure theorem of the automorphism group or real algebra of automorphism group. So there is a map from the so G node is a subgroup, and there's a map from the J to the H1. So this is by this map is given by spin representation of the element of the A on the Gj. Gj is acting on the psi. This is a spin representation, also acting on the psi bar. So then, if the A is the element of the d bar A equals 0, then this is also element of define the class of the H1. This map J is just a kind of the generalization of the Albanese map in Kähler geometry. So that this is also we can see that this part is just a abelian group. So that we support the natural structure theorem of the automorphism groups of the algebra of general Kähler manifold. So that this theorem is a point of the this code. If the scalar curvature is a constant, then this real algebra, reduced real algebra here is just reductive. So also we can have the let Mj be a 2n-dimensional compact generalized Kähler manifold. If the H1 is equal to 0, then the Gj coincides with the reduced one. So if M admits general Kähler structure of symplectic type with constant scalar curvature, then this one is also reductive. And this is a very interesting, important case. So let Mj be a compact Kähler manifold with harmonic Poisson structure, not trivial from Poisson structures. We assume the M is H1 vanishes, then we have a deformation of the general Kähler structures, which is given by Poisson structures. So if the scalar curvature is a constant, then the real algebra of the automorphisms of the general complex structure J beta is a reductive real algebra. In this case, so this automorphism group is just coincide with the automorphism group preserving the Poisson structures, so that we can calculate this one explicitly. So this is a key proof of the key point of theorem 7.10. Our main theorem here. The proof is quite similar. We use a certain kind of the operator of the L. So this is a differential operator of the fourth degree, and consider the conjugate one. And this is a key point of this is a kind of the Poisson bracket for U and Sj. Poisson bracket is given by the difference between L minus L bar. Then if the scalar curvature is constant, then this is equal to 0. So that the Lu is equal to L by U. So that if the U is a function given by real part, this imaginary part, and satisfied here, and satisfied Lu equals 0, then from this one, real part and the imaginary part also satisfied Lu LU imaginary vanishes. So that G naught is given by the complexification of the reductive real G0 R. So that's G0 is also reductive. That is a proof. So in the case of CP2, so as I explained at the first part of my talk, we can calculate automorphisms of the generalized complex manifold Gj. So there's a 9. So let Mj be a complex projective space CP2 with a beta Poisson structure of the X, and M did not underline differential manifold. And since beta is a holomorphic section of the anti-canonical line boundary of X, so that beta is given by a homogeneous polynomial of the degree 3, that's a cubic curve. So the cubic curve is corresponding to 9 cases. So as I assumed that. Then this case is a reductive. But this red one is not reductive, non-reductive. So we can have a obstruction. So these 3 cases, red one, so does not admit any general Kähler structure with constant scalar curvature. This is a calculation of the automorphism group of the Lie algebra, so generally complex manifold. So, but I'd like to skip here. So in the case of CP2, so generally complex project surface beta is given by figure 789. Then CP2JB does not admit any general Kähler structure with constant scalar curvature. So this is just obstruction. So also we need to say if in the case of the blue one, so this case, so there is a general Kähler structure with constant scalar curvature in this case. But I don't know in the other case, so I don't have I cannot construct any general Kähler structure with constant scalar curvature in case of the figure 1, 2, 3, 4, 5. So final part of my talk, I'd like to construct a kind of like give the existence result of the general Kähler manifold with constant scalar curvature. So let J and psi be a general Kähler structure of symplectic type of the compact manifold M with constant scalar curvature. No, sorry, this is wrong. This is ordinary Kähler manifold. And we assume the scalar curvature is constant. We assume the algebra of reduced automorphism G not is trivial. Then so we have a kind of deformation of the general complex structures, and there exists deformation of the general Kähler structure with constant scalar curvature for sufficiently small t. So that if the general Kähler manifold, ordinary Kähler manifold with constant scalar curvature and the automorphism group is trivial, and then by using Poisson structure, we can have a non-trivial general Kähler structures with constant scalar curvature. So that is also example. Let Mj be a compact Kähler manifold with constant scalar curvature. We assume that the reduced automorphism is trivial. If there exists a non-zero Poisson structure beta on Mj, then there exists a deformation of general Kähler structure with constant scalar curvature. In particular, so derivative surfaces with trivial automorphisms admit a general Kähler structure with constant scalar curvature. For instance, so if we consider the CP2 and the cubic curve, elliptic curve, and consider the blown-up elliptic curve at 6 point. An end point. P1, P2, Pn. N is just a Then this is also CP is blown up the endpoint, admit Kähler structure with constant scalar curvature. And also we have a Poisson structure beta. It's just given by anti-canonical divisor of this one, elliptic curve. So that in this case, so by using this one, so also CP blown up the n is greater than or equal to 4, and automorphism group is trivial. So that we can apply this theorem, and there exists a general Kähler structure with trivial, with constant scalar curvature in this case. So that there exists this is the existence result. Okay, so I stopped my talk here. Thank you very much. So thank you very much for listening.
Thank you very much for the talk. So let's open the questions in the room. Okay.
So good evening, Goto-san. So it's a bit late.
Good morning.
So in the classic Matsushima-Lichnerowicz theorem, the punchline can be interpreted as saying that actually there's a compact real form, namely the isometry group, to the complex automorphism group. So your argument here in this generalized Kähler case is all on the level of the Lie algebra, but I was wondering, is there some sense in which you can exponentiate the action and understand? I mean, the sense in which you've been talking about the automorphism algebra is somewhat formal from at least on first hearing, and I was just wondering if there's a more, is there actually something you can say on the level of Lie groups rather than Lie algebras?
Yes, I don't have any answer about that, because in general Kähler case we consider the cohomology groups of some Lie complex. So then in the Kähler case, automorphism group act on the manifold, But in general Kähler case, so we consider the cohomology group. So such a cohomology group does not act on the manifold. So that is very different. So yeah, here we consider cohomology group. So and even in the Kähler case, so we need to consider this part. So here. So this does not act on the manifold. So yeah, but we need to consider some kind of bundle map of Tm star. So then this group act on here this here as a bundle map, I think. So then we can consider that similar way, but I don't know. So
one reason I raised the question is that when you look at deformations of constant scalar curvature Kähler metrics, do things when the automorphism group is non-trivial, provided you fix a maximal compact, then the theory goes through pretty much. If you look at deformations that preserve the same automorphism group, then then the deformation theory works the same. The thing that tends to go wrong, though, is that most deformations change the size of the automorphism. Anyway.
Yes.
Very interesting results.
So I need to say, so I apply the deformation theory. You Crowd, Lebrun, and Szymanski. This is quite similar. So.
Thank you. Restislav, can you make?
Yes. I have a question. Can you consider also extremo generalized Kähler metrics? And more particularly, my question is the following: in these three examples on CP2, where you observe that there are no constant scalar curvature metrics because the Lie algebra is non-reductive.
Yes.
Do you think we can expect extremal generalized scalar metrics in that case?
I think, I think that's kind of a Hessian formula of the, so that we have this similar kind of the decomposition formula of the algebra of automorphisms, general Kähler manifold, extremal case. So I think probably we can apply the similar kind of the obstruction theorem to the extremal case, I think.
Yes, the Scalar curvature in that case will be central. And you need to consider an algebra centralizer and see if it's reductive or not.
Yeah.
So did you try to detect the center in these cases and to see that the quotient is?
The calculation is a very simple calculation. So we just in this case the automorphism group, just automorphism group, so preserving the cubic curve. So that's this is just a calculation like that. So this automorphism group is given by like that. So I think it is possible. I think, but I'm not carried out in yet. So.
Thank you.
Yeah.
Leo, you're next.
Yes. Hello, Ryushi. Once you have this Lichnerowicz Matsushima obstruction, the next would be for Kähler geometry Futaki invariant. Do you think there is any analog for generalized?
Yes, I think so. The scalar curvature arises as a momentum, so we can define this Futaki invariant. So as in the case of the Kähler geometry. But the point is, yes, answer yes. So we can define Futaki invariant by using scalar curvature as a moment map pictures. But I don't know about this. So good example of such obstruction actually effective. So I don't have now. I don't have a good example. So.
Okay. Yeah. I see. Thank you.
Yes, thank you.
Any further questions out there in our Zoom room or here in the lecture hall? No, doesn't seem to be the case. So thank you very much. And
thank you very much.